It's all about energy. We know that real-world conditions can create certain loss factors that limit the actual performance of a solar module. But there are several other technology-specific loss factors that come into play. For starters, there's temperature, which can have a major effect on how well your solar installation performs. A metric called temperature coefficient measures changes in the efficiency and power output of a module as temperature increases. All PV modules, regardless of their technology, see a reduction in power and efficiency as temperatures rise above 25 degrees Celsius, which is the standard test condition temperature for solar modules. Temperature coefficient becomes especially important in hot climates, where modules can spend more than 90% of their generating hours at temperatures above 25 degrees Celsius. Temperature coefficient is a key consideration in selecting the solar technology that's best suited for hot climates. CdTe modules, for example, can produce up to 4% more annual energy in hot climates because they're far less sensitive to increases in temperature when compared to crystalline silicon modules. Another factor to consider is shading response, a measure of how well a solar module performs in partial shading conditions caused by trees, buildings, clouds, or other obstructions. Even a small amount of shading can reduce the power output of a solar module due to the way the cells are connected in series and parallel circuits. That's why crystalline silicon modules are often designed in a way that can redirect current around any shaded cells. In an environment with 10% linear shading, a standard crystalline silicon module can lose up to 50% of its power output, while a CdTe module loses only about 10% due to its electrical design. On an annual basis, this adds up to as much as 1% more energy when compared to crystalline silicon modules. Light-induced degradation, or LID, refers to the initial drop in performance that crystalline silicon modules experience shortly after being exposed to sunlight for the first time. This drop-off, which occurs in the first few hours or weeks of exposure, can result in a loss of efficiency up to 3%. A drop-off of this magnitude can have a significant impact on the overall energy yield and ROI of a solar installation over its 30-year lifetime. Light and elevated temperature-induced degradation, or LETID, occurs in crystalline silicon modules exposed to both sunlight and elevated temperatures. Unlike LID, which occurs after an initial exposure to light, LETID occurs over an extended period and at higher operating temperatures. Over time, LETID can lead to a reduction in the efficiency of crystalline silicon modules of 3 to 6%. However, the impact of LID and LETID can be avoided by choosing a solar module technology such as CdTe that's immune to these loss factors. A solar module's long-term degradation rate refers to the gradual decline in its performance and efficiency over time. It's a natural and expected occurrence that affects all types of solar modules, although the rate of degradation can vary based on the materials used, certain environmental conditions, and the quality of manufacturing. Even a small difference in the long-term degradation rate can have a huge impact on energy yield and ROI over the course of a 30-year product lifetime. It's easy to see why efficiency ratings are an incomplete measure of solar module performance. Efficiency ratings represent the percentage of sunlight that a solar module converts into usable electricity without considering the wide range of loss factors that impact overall energy performance. They don't factor in how well a module performs in less than optimal conditions, such as partial shading, high temperatures, or high humidity. And they don't capture a module's ability to resist degradation factors like LID and LETID. So, what's the most comprehensive way to assess the long-term energy performance of a solar module? Specific energy yield. This is the only way that accounts for a solar module's output power through the full range of real-world conditions, while also factoring in technology-specific performance characteristics. Using energy prediction software like PlantPredict or PVsyst makes it easy to calculate specific energy yield for your solar project. It's the best way to get the insight you need to select the solar technology that's right for your project, because it's all about energy.